problem. And thank you to the organisers and for a great workshop and for letting me drag you back from lunch to tell you about some recent work that I've done with Sylvia. So this is going to be a talk about the renormalization of free field theories on a curved space-time background. And for example, for considering expectation values of observables such as the stress energy tensor operator. Now, one way of doing this is to take the Green's function, which depends on two space-time points x and x primed, apply to this a linear second-order differential operator, and then take the limit in which you bring the points together. Now, if you do that, you will end up with an infinite answer because the Green's function itself is singular in the coincidence limit when we bring the points together. So we're going to consider renormalization as identifying singular parts of the Green's function which diverge in the coincidence limit, subtracting these from the Green's function to leave something that is then regular and gives you a renormalized expectation value. Now, there are lots of different approaches to identifying these singular terms. This afternoon, I'm going to consider just three. And we're going to address the question that I think is going to disappear off the bottom of the slides with this resolution. Sorry about that. About whether these three approaches give you the same answer. Now, this is not a trivial question because, as I like to put it, do you subtract infinity or infinity plus 1? You can always include some bonus regular parts in your singular part before you subtract it. And the model that we're going to consider is that of a free charged scalar field. This is going to have charge little q, mass m, and coupling psi to the Ricci scalar curvature. Nabla is the usual space-time covariant derivative. And in addition to a fixed classical space-time background, I also have a fixed classical electromagnetic field with potential A mu. And the three approaches to renormalization that I'm going to be considering have been studied in the literature: deWitt-Schwinger, more recently adiabatic, and more recently still Hadamard. So let's look at each of these in turn. So Hadamard renormalization is based on the Hadamard parametrics. And to keep the algebra manageable, this afternoon I'm just going to consider two or three space-time dimensions. So this is the form of the Green's function. It depends on various biscalars. So the first of these is sigma, Singe's world function. This is equal to 1/2 of the square of the geodesic separation between the points. So in the coincidence limit, when I bring the points together, sigma will go to 0. And you can see that in both 2 and 3 dimensions, I will have a singularity in the Green's function. L is a length scale introduced purely so that the argument of the logarithm is dimensionless. U, V, and W are Hadamard biscalars. They are regular in the limit in which I bring the points together. And they depend, U and V, are determined purely by the background space-time geometry and the background electromagnetic potential. Now, at least formally, we can write those as a power series expansion in powers of the world function sigma, and we can find the coefficients U and V by solving a set of recurrence relations, and we can work to whatever order we want. W, on the other hand, is not fixed in this formalism. And in general, that will depend on the quantum state. So now let's turn to deWitt-Schwinger renormalization. So the singular parts of the Green's function, in this case, I'm going to call G ds. And here is the form that they take. So they're given as an integral over a quantity s. N here is the number of dimensions. I've got the world function, sigma again. Epsilon is just a regulator. Scalar field mass. And I have a set of deWitt-Schwinger coefficients that I've called curly AN. So these are, like the Hadamard coefficients, are regular in the coincidence limit. They're determined just by the background geometry and the background electromagnetic field. And just as with the Hadamard biscalars, I can find these to whatever order I want by solving a set of recurrence relations. So far we've had two approaches to renormalization. We started with the Hadamard parametrics for the Green's function, and then we've introduced the deWitt-Schwinger Green's function. Now these look very different. However, we know that U, V, and the curly A's can be found by solving a set of recurrence relations. And in fact, we can use those recurrence relations to show explicitly that GDS has precisely the Hadamard form with a particular non-zero W. And we have a closed form. I mean, it's not very nice, but we have a closed form expression for WDS, and it can be found explicitly. So one thing I've learned so far today, I've learned lots about quantum field theory. I've also learned that I need to change my Beamer template to 16:9 resolution. Right. Okay. So that's, well, we can argue about which is the more useful thing to have learned. This was shown for a neutral scalar by Decanini and Fallaci, and we've extended that to the charged case. Okay, two methods of renormalization down. Everything I've said so far is valid for any space-time background, any background electromagnetic field, and any point splitting. For the rest of the talk, I want to consider one particular background, flat FLRW. And here's the form of the metric in Cartesian coordinates. A here is going to be the scale factor, and I'm assuming that I have a background time-varying electric field with potential big A. So as we saw before lunch, I can write my charged scalar field as a mode sum. So B and D are annihilation and creation operators. Because I have a flat FLRW, the spatial parts of my mode functions are simply given by plane waves with wave number k. And the other part of my modes are these time-dependent functions h. So I'm also now going to exploit the symmetries of the background and consider points that are split only in the spatial directions. And if I do that, thank you, this is the form that the Green's function will take. So it depends on the spatial separation of the points and an integral over the square of these time-dependent functions. So I'm now in a position to turn to my third method of renormalization, adiabatic renormalization. So here, the singular parts of the Green's function, I'm imaginatively going to call G adiabatic. So how do I find these? Well, I'm going to perform an adiabatic expansion of these mode functions H. It's a bit like a WKB expansion. And I write them first in terms of big omega and then in terms of little omegas. And the little omegas I can find algebraically using an iterative process. They are given purely in terms of the scale factor, the electric potential and derivatives of these. And a bit of terminology, we say that the nth little omega is of adiabatic order n. And one thing that we're going to need later is that if I perform a derivative with respect to time, each time I make a time derivative, then I increase the adiabatic order by 1. And in order to perform adiabatic renormalization, I need to include all the terms up to and including adiabatic order equal to the number of space-time dimensions. Okay, so now let's compare adiabatic and deWitt-Schwinger renormalization. So I'll just remind you, there's the deWitt-Schwinger Green's function. Here is the adiabatic Green's function. And they look very different. So how am I going to compare these? I'm going to perform a direct computation. So I'm going to spare you the details. Here's the general strategy. So considering first the adiabatic Green's function, I evaluate all the little omegas up to the order that I need. I then do my integral over the wave number to find the Green's function. And finally, I'm going to perform an expansion up to the order of the square of the separation in the points. Now, the reason for doing that is that in order to find the stress energy tensor, I need to differentiate the Green's function twice before I bring the points together. For the deWitt-Schwinger Green's function, I have that very general expression. So I restrict that to space-time, space-like point splitting on FLRW. I can find the U and V Hadamard biscalars by solving the recurrence relations to the required order. And I can find the third biscalar W, again to the required order, using my horrible algebraic expression that I didn't show you. So what are the answers that we get? Well, let's consider first two space-time dimensions. And here's the expression that we get for the adiabatic Green's function. Don't worry, you don't need to pass it all. It depends on the separation. Gamma is Euler's constant. It depends on the mass, charge, and coupling of the scalar field, and also depends on the scale factor A, electric potential, big A, and its derivatives. Fine. Now, this is the moment of truth. Here is what we get. Oh, it just fits on, brilliant. Here's what we get for GDS. Okay. Now, again, I don't expect you to pass it, but take my word for it. These two match exactly. So in two space-time dimensions, adiabatic and deWitt-Schwinger identify exactly the same singular terms in the Green's function. Excellent. Let's move on to 3 dimensions. Now, okay, you don't need to pass that. This is the deWitt-Schwinger Green's function. Okay, fine. So suffice it to say that if you calculate the adiabatic Green's function, every term in here agrees except for the 4 terms on the bottom line, which fortuitously I put on the next slide. That was a stroke of genius, wasn't it? Okay. So I've got these 4 extra terms. So these are terms which appear in the deWitt-Schwinger Green's function, but not the adiabatic Green's function. They're all order epsilon squared, the square of the separation of the points, and this means that they will make a finite contribution to the renormalized stress energy tensor. They are all of adiabatic order 4. Those of you with good memories remember that a time derivative increases the adiabatic order. So these have all got 4 time derivatives in them. And this is why they're not in G adiabatic, because we only calculated the adiabatic Green's function to order 3 because I'm in 3 dimensions. And interestingly, these don't depend on the electromagnetic potential. So one thing I neglected to say was that in 2 dimensions, the agreement between adiabatic and deWitt-Schwinger regularization was already known. We've just extended it to the charged case. But these terms appear for a neutral scalar field as well. So, to summarize, we've looked at the process of renormalization for a charged scalar field on flat FLRW. And we've considered this by identifying singular terms that we want to subtract from our Green's function before we apply differential operators to find expectation values. And we've looked at 3 approaches to renormalization. Firstly, we considered the Hadamard parametrics for our Green's function, and we were able to show that the deWitt-Schwinger Green's function has precisely the Hadamard form for a particular choice of the biscalar W. Thirdly, we have considered adiabatic renormalization given by the adiabatic Green's function, which has a very different form. So by direct calculation, I've shown you the results in 2 space-time dimensions. Even if I'd got the aspect ratio correct, the results in 4 dimensions wouldn't have fitted on one slide. But we find exactly the same result in 4 dimensions, namely that the deWitt-Schwinger and adiabatic Green's functions agree precisely. So in 2 and 4 dimensions, these are equivalent methods of renormalization, which is always reassuring. It's good to know that you're going to get the same answer no matter which method you use. However, in 3 dimensions, what we found is that the deWitt-Schwinger Green's function contains extra terms which are not present in the adiabatic Green's function. So in this case, it's not clear that these 2 methods of renormalization are equivalent. And given that that's fallen off the bottom of the slide, we'll leave the interpretation of those extra terms for another time. Thank you.
Thank you for this nice talk. We have time for a couple of questions.
Thank you for a very nice talk. I wanted to ask, the extra terms that you show, it looks like in the conformal coupling case, they go away. Is there any intuitive reason why we should expect that to happen?
So this is exactly what I thought at first. I thought, oh, if you put psi equal to a 6, they disappear. This is in 3 dimensions. So psi is an 8th is conformal coupling. Yeah.
Disappointing.
Yeah.
Yeah, thanks also for me again for this nice talk. You work to order epsilon squared. Are there maybe arguments also at higher orders in, say, even dimensions where they agree?
Oh, that's a really good question. So the short answer is I don't know because I've not calculated the terms. There may well be discrepancies at higher order as well. I mean, you wouldn't expect the Green's functions to agree at every order, I don't think. But certainly, yeah, it wouldn't surprise me.
Thanks.